Good morning. Today we will start Newton-Raphson method of load flow. In previous classes, we have studied Gauss-Seidel method of load flow. The question is, why Newton-Raphson method of load flow? Newton-Raphson method of load flow is having certain advantages, like it's faster. You can write faster than Gauss-Seidel method of load flow. Second, it's a powerful method for solving non-linear algebraic equations. So first we will learn what is Newton-Raphson method in general, then we will apply for load flow. Consider a set of n non-linear algebraic equations denoted by Fi. We can write a design vector x equal to 0. Fi is a function of x where I equal to 1, 2 up to n, means we are having n number of non-linear algebraic equations in x, where x is design vector having n design variables x1, x2, xn. The same algebraic function can be represented by, say, if x fi x1, x2, xn is equal to 0. So for I equal to 1, we will get f1 function of x1, x2, xn. Similarly, for I is equal to 2, 3, n, fn will be equal to fn x1, x2, xn equal to 0. So we have to solve these functions, n number of functions, using Newton-Raphson method. We are having our unknowns as x1, x2, x3, xn. We want to get the solution of these variables. Suppose initial guess for the variables is given by x0, that is nothing but x1 0, x2 0, xn 0, initial guess. Initial guess may not be feasible, but at least we have to consider the values which are close to solution, we can guess it. Once the corrections are added in initial guess, then we will get the solution. Say the corresponding corrections are del x0, del x1 0, del x2 0, del xn 0. Means the corrections once added with the guess values, we will obtain the solution. Then our algebraic equations can be written as x1 plus del x1 0, comma del x1 0 added with x1 0, x2 plus del x2 0 and so on, xn plus del xn 0. So, it will satisfy, means once substituting these values, it will satisfy the set of n equations I equal to 1 to n. So, for all the equations using Taylor series expansion, we can write f I, this is 0, initial guess values. So, we can write f x1 0, comma x2 0, comma xn 0 plus first derivative of this with respect to x1, we can write partial derivative del f I upon del x1 evaluated at x equal to x0 initial guess times del x1 0 plus del f I del x2 evaluated at initial guess values x0 times del x2 0 plus so on plus nth term del f I del xn evaluated at x equal to x0 times del xn 0 plus higher order terms, equal to 0. What are these? F I equal to 1 to n denotes n number of non-linear algebraic equations, and x1 0, x2 0 up to xn 0 are the initial guess values for our variables, n variables. So, when the corrections del x1 0 corresponding corrections, del x1 0 is correction in x1 0, del x2 0 is correction in x2 0. When the corresponding corrections are added with initial guess, we will get the solution, but we do not know the values of these corrections, that will be calculated, we will see later. So, using Taylor series expansion, we can write this. Neglecting higher order term, in matrix form, we can write say for I equal to 1, first row will be written. So, here we can write f1 say x0, these are initial guess. So, f1 I equal to 1 evaluated at x0 will be written as f1 x0, f2 x0, so on. For I equal to n, we will get fn x0 plus this plus. For I equal to 1, this will be f1 f1 so on. So, first row will be written as del f1 upon del x1 evaluated at x is equal to x0 times del x1 0. Next will be del f1 upon del x2 evaluated at x equal to x0, we may have this and so on, del f1 upon del xn evaluated at this was del x2 0 evaluated at x is equal to x 0 del x n 0. First row, similarly second row will be del f2, second row is corresponding to I is equal to 2. So, for I is equal to 2 we are having f2 x 0 plus sign is here, and then I is equal to 2, here we will write del f2 upon del x1 evaluated at initial guess values del x1 0 del f2, or better we can multiply this del x1 values here in matrix form, we can write here itself. So, remove this from here and put directly here del x1 0 del x2 0 del xn 0. We know the matrix multiplication rule. These two matrices are multiplied. So, once this row is multiplied with this, so we will get this times the same which earlier we were getting here. So, del f1 upon del x1 x is equal to x 0 times del x1, because it will come in each row. So, directly here we can write del f2 upon del x2 x is equal to x 0 and so on, del f2 upon del xn x equal to x 0. Write the nth term, nth row. So, for I is equal to n, we will get the nth row here del fn upon del x1 x equal to x 0, remove this because we have taken care there, del fn upon del x2 x is equal to x 0 and so on, del fn upon del xn x is equal to x 0. Clear? We have neglected higher order terms, means 0. So, directly this can be written as is equal to 0. For the same Taylor series expansion, we have neglected the higher order term, and for I equal to 1 to n, because in the beginning we have assumed that we are having n number of non-linear algebraic equations. So, for all algebraic equations starting from f1, f2, fn, we can write this plus sign is here and this one del x1, del x2 0, del xn 0, like that, equal to 0. The same we can write f0, the same we can write this is f0, say this is f0, this matrix J0 denote it by J0, and for this denote by del x0. So, we can write f0 plus J0 times del x0 equal to 0. So, we can write here f0 plus J0 del x0 will be equal to 0, or we can write f0 will be equal to minus J0 del x0, where J is Jacobian matrix evaluated by taking partial derivative with respect to x, capital X design vector, and evaluated at x is equal to 0, this one. So, from here we can also write del x0 is equal to this one, del x0 will be equal to, send this to this side, means inverse of this. So, minus J0 inverse times F0. This del x0 is equal to minus sign here inverse and F0. So, this way we have evaluated the corrections required to be added in the initial guess value to get the desired solution. So, say the updated values of the design variables x may be written as, say for first iteration x1 may be written as initial guess is x0 plus corrections del x0, where del x0 is given by this. For rth iteration, from here we can write, for rth iteration we can write xr is equal to previous iteration value x r minus 1 plus del x r minus 1. This way in each iteration we will calculate this and we will update this, where del x we can write here itself, where del x r minus 1 can be written from here. Del x 0 is this one. So, del x r minus 1 may be written as minus Jacobian matrix evaluated in previous iteration r minus 1 inverse this one times f r minus 1. These two relations are important. So, calculate this del x and update this. So, when should we stop? When we are close to solution, we should stop iteration. So, how to decide whether we have reached the solution or not? That will be decided by evaluating this. Initially, whatever we have assumed, we are calculating f0. In the next iteration, we will get f1 corresponding to this. So, in rth iteration, we are having f r minus 1. So, after evaluating del x r minus 1, we will get x r. So, substituting this x r in our functions, we will get, suppose for function 1, we will get f1 x r. For function 2, we will get f2 x r and so on. Grab this. For nth function, we will get x r. So, take maximum of this . Say this is tolerance, say TOL, tolerance is equal to maximum of this. If this tolerance is equal or less than some, say epsilon, maybe 10 to the power minus 3, minus 6, etc., which you can tolerate, 10 to the minus 12. So, if this tolerance is equal or less than certain specified value, say 10 to the minus 3, 10 to the minus 6, minus 12, whatever you can tolerate, we have to stop there, and the updated XR will give the solution. Updated XR means we are having our design vectors x. So, corresponding to XR, we will get x1 r, x2 r, xn r. These are our solutions.